Thank you, Chairman, for introducing me. Hello, everyone. My name is Seong-Jin Im, and I will present my paper about the reliability of snowball circuit. First page for the contents. I will present the research purpose and study gate in the introduction section. Next, we calculate the part failure rate by using LSTM and mission profile. And we calculate the module and system failure rate by using Markov model. And the last section is for the conclusion. First page for the introduction is the DC storage state circuit breaker is the snowball circuit by figure 1A to reduce surge voltage. The more snowball circuit combines like figure 1B, C, D, and E, the surge voltage reduces more and more, like shown in figure 2. But the number of components increase, the failure rates also increase. So we need to analyze the reliability of the snowball circuit. Conventional method fix the temperature and humidity parameter, so the failure rate also fixed. But the temperature and humidity change every day, so we need to have a time-dependent failure rate. This paper reflects the actual data of temperature and humidity predicted by LSTM to calculate the dynamic failure rate. And we build the mission profile according to the circuit operation to improve the accuracy. This page for the LSTM. Table 1 shows the LSTM model setup specification. I will present the main parameter of LSTM. First, number of epochs is set up to 300. That means the entire training data is 300. Second, the sequence length is set up to 5. That means LSTM run 5 data points and predict the next data. We set up the sampling time by 10 days. So for example, LSTM learning up to 50 days and predict up to 60 days. And we want to know the temperature and humidity, so the input and output sides set up by 2. The number of days for the future prediction is set up by 6 years, so the LSTM predicts the 6 years data without the actual data. And LSTM calculates the loss based on the mean squared error called NSC, and we use the ADEM optimizer to quickly find the optimal point. This page for the result of LSTM. Figure 3 shows the training and validation loss according to the number of epochs. The LSTM separates the actual data into training data and validation data. Training loss means the error between training data and prediction data. It used for update running parameter. Validation loss means the validation data and prediction data is error. It used for only validation. Figure 4 shows the ambient temperature and humidity predicted by LSTM. First 6 years, LSTM predicts the data with actual data. And next 6 years, LSTM predicts the data without actual data. And next section is for the mission profile. The mission profile is divided into operation base and stop base according to the circuit operation shown in figure 5. The operation base consider about the summer factor and not consider about the humidity factor. But stop base consider the humidity factor and not consider about the summer factor. Some part divide the operation base into additional base according to the operation condition. This page for the most effective mission profile. The most effective operation base divided into normal phase and failure phase. The main parameter of most effective summer factor is the junction temperature calculated by ambient temperature and junction to ambient summer resistance, switch current, and on-state resistance. The total parameter failure rate calculated as sum of each failure rate of each page. Figure 6 shows the most effective time-dependent failure rate. Next page for the MOV mission profile. The main parameter of MOV summer factor is the power ratio between applied power and rated power. Figure 7 shows the MOV time-dependent failure rate. Next is for the resistor emission profile. The main parameter of resistor sum factor is also power ratio. Figure 8 shows the resistor time-dependent failure rate. Next page for the capacitor emission profile. The main parameter of capacitor sum factor is the voltage ratio between applied voltage and rated voltage. Figure 9 is the time-dependent failure rate of capacitor. Next page for the diode emission profile. Diode operation phase divided into forward phase and reverse phase according to the diode current and diode voltage. Figure 10 shows the diode time-dependent failure rate. Next section is for the Markov model. The Markov model considers all possible processes from normal state to complete failure state. Markov model has 4 modules, including MOSFET, 2 MOVs, and RCD number. If any of the resistor, capacitor, or diode fault, the RCD number function fault. So we calculate the RCD number failure as sum of each part. The component normal state represented by 1 and component failure state represented by 0. The system normal state represented by black and system failure state represented by red. The first definition of system failure is the surge voltage production increase more than 3%. According to the table 7, the more than 2 components fault, the surge voltage production increase more than 3%. And the last definition of the system failure is the MOSFET failure state. Because when MOSFET fault, the circuit breaker function fault. And we calculate the module failure rate by a sum of each probability of system normal state. Figure 12 shows the time-dependent failure rate of entire snubber circuit. The last section is for the conclusion. We analyzed the reliability of snubber circuit by LSTM, mission profile, and Markov model. And the SSCB snubber circuit lifetime is more than 12 years because the number of SSCB operation is very low compared to the general electronic system operation. And we plan to make a redundancy module to increase component margin to purpose effective snubber design by comparing reliability and price. Thank you for listening.
Thank you very much.